Okay, now I would like to explain about the action of commutator. Okay, in last video we discussed the operation of simple loop generator with the slip rings. So now in this case, this is also one simple loop generator. Here slip rings are replaced by commutator. Okay, this is called commutator or split rings. The purpose of the commutator, which converts the AC supply into DC supply. The commutator is made up of copper material and it having number of copper segments. So each segment is separated by the mica material. Okay, this is mica material insulation. So in last video we discussed the operation of simple loop generator. We know that at position 1, at different positions we studied dynamically induced EMF. Okay, at position 1, the conductors are moving parallel to magnetic field. So dynamically induced EMF value equals to 0. Next position 2, the conductors are moving perpendicular, so theta value 90 degrees. Dynamically induced EMF value maximum value, it equals to BLV. Again at position 3, conductors are moving parallel to magnetic field, so dynamically induced EMF value 0. So next to position 4, the dynamically induced EMF value maximum value. At position 5, the dynamically induced EMF value equals to 0. In case of slip rings, in position 2 and position 4, the dynamically induced EMF values, maximum values, position 2 maximum value, it equals to BLV, and position 4 also maximum value, it equals to BLV. So but in position 2 and position 2, the current directions are reversed. In position 2, the current flows from P to Q in external load. In position 4, the current flows from Q to P in external load. So current direction reverse in position 2 and in position 4. So the generated EMF is AC supply, or it is also called as bidirectional voltage. So but in this case, by replacing slip rings by commutator, so we get DC voltage or unidirectional voltage. So here C1, C2 are called commutator segments. So here also same, in position 1, the conductors are moving parallel to magnetic field. So the rate of change of flux linkage is equals to 0. So theta value equals to 0, the dynamically induced EMF value equals to 0. Okay, so next in position 2, so the conductors are moving perpendicular to magnetic field, theta value 90 degrees, rate of change of flux linkage is maximum, so dynamically induced EMF value equals to BLV. So in this case we have to find the direction of the current by using Fleming's right hand rule. So by applying Fleming's right hand rule, so we get the current direction in CD conductor from D to C and in AB conductor from A to B. So the total current direction inside the generator is from D to C, C to A to B, B to C2, C2 to B2, B2 to Q, Q to P, P to B1, B1 to C1 and C1 to D. Okay, this is the current flow inside the generator. In external load, the current direction from point Q to from point P. So next to position 3, in case of position 3, we know that the conductors are moving parallel to the magnetic field. Okay, after 90 degrees from position 2, the conductors are moving parallel to magnetic field, so theta value 0, dynamically induced EMF value 0. So next again after 90 degrees of rotation, the position 4, in position 4, this is the conductor's position. Okay, so this is AB conductor and this is CD conductor. Now see the main difference between second position and fourth position. In second position, the commutator segment C1 connected to B1, commutator segment C2 connected to B2. Okay, so here also AB connected to C2, CD connected to C1. Here also same, AB connected to C2, CD connected to C1. So the main difference is in position 2, the commutator segment C1 connected to B1, C2 connected to B2. But in position 4, the C2 connected to B1, C1 connected to B2. So the brushes are stationary parts. Commutator is a rotating device. After 180 degrees rotation, the C1 and the C2 positions becomes like this. Positions are interchanged. But in previous case, the simple loop generator operation with slip rings, S1 is permanently connected to B1, S2 is permanently connected to B2 in all positions. Position 1 to position 5, in all positions, S1 permanently connected to B1, S2 permanently connected to B2. But in this case, if we replace slip rings by commutator in position 2 and position 4, okay, after 180 degrees rotation, the commutator segment positions are interchanged. In position 2, C1 B1 connected, C2 B2 connected. In position 4, C2 B1 connected, C1 B2 connected. So because of these connections, the external load direction in position 2 and position 4 is same. Okay, see, in position 4 the conductors are moving perpendicular to the magnetic field, so theta value equals to 90 degrees. The dynamically induced EMF E equals to BLV sin 90, sin 90 equals to 1, so E value equals to BLV. So now find the current direction by using Fleming's right hand rule. In AB conductor, the current flows from point B to point A. In CD conductor, the current flows from point C to D. In total generator, the current direction B to A to C, C to D, D to C1, C1 to B2, B2 to Q, Q to P, P to B1, B1 to C2, C2 to B. Okay, this is the current flow inside the generator. Now see, in external load, the current flows from point Q to point P, point Q to point P in external load current direction. In second position, in external load current direction Q to P. In fourth position also, in external load the current direction is Q to P. So if we use slip rings in place of commutator in position 2 and position 4, the current directions are opposite. If we replace slip rings by commutator in position 2 and position 4 in external load, the same current direction is there. So now draw the graph between generated voltage with respect to time. Okay, these are the different positions. So first at position 1. So position 1 generated EMF value 0. Position 2 generated EMF value maximum value, it equals to BLV. So next at position 3 EMF value 0. So next at position 4 the EMF value maximum value, it equals to BLV, and in second direction, fourth direction, current direction is same. So position 2 and position 4 the generated voltage polarity also same. Okay, so current direction reverse means the polarities of voltage is reversed. Current direction same means same polarity voltage generated. So here position 2, in position 2 the generated voltage is positive, so position 4 also the generated EMF polarity is positive. Okay, so next at position 5. So position 5 means position 1. So position 5 is same as position 1. After 360 degree rotation, again the coil reaches to position 1. Okay, so position 5 is same as position 1. At position 1 the dynamically induced EMF value equals to 0. So finally this is the graph between generated EMF versus time. So this type of voltage is called unidirectional voltage. Here only positive half cycle is there. Okay, if only negative half cycles only there, that voltage also called unidirectional voltage. If both positive and negative cycles are present, the voltage is called bidirectional voltage. Okay, this voltage is unidirectional voltage. So total 5 positions. In position 1, position 3 and position 5 the dynamically induced EMF value 0. In position 2 and position 4 dynamically induced EMF values maximum values and current flows in same direction. So finally this is the generated EMF waveform. Okay, here number of commutator segments equals to 2, number of conductors equals to 2. So we get waveform like this. Okay, if we increase number of conductors, then automatically number of commutator segments also increases. So then this unidirectional voltage is converted into pure DC. If we increase more number of commutator segments, the waveforms becomes like this. If we increase again more number of conductors and commutator segments, we get pure DC. So finally we can say that, so by replacing slip rings by commutator, so we get DC supply. So this is one simple loop DC generator. So commutator is a main part of a DC generator, so which converts the AC supply to DC supply in case of generator. So same commutator converts the DC supply to AC supply in case of DC motors. Okay, so in case of DC generator it converts the AC supply to DC supply. In case of DC motors, which converts the DC supply to AC supply. In case of DC generator it is called mechanical rectifier, but in case of DC motors the commutator is called mechanical inverter. Okay, next topic, EMF equation of DC generator. Okay, so first let the pi is flux per pole. So flux units Webers. Okay, next capital Z is total number of armature conductors. it equals to number of slots into number of conductor per slot. So next P is number of generator poles. Capital A is the number of parallel paths in armature. So next capital N is armature speed. So armature rotation in RPM. So RPM means revolutions per minute. So next capital E is generated EMF or EMF induced in any parallel path in armature. So generated EMF EG equals to EMF generated in any one of the parallel paths, that is E. So EG equals to E. So the average EMF generated per conductor according to the Faraday's law of electromagnetic induction, the average EMF generated per conductor equals to d pi by dt. Okay, this is d pi by dt. Okay, d pi by dt. This one here dt. Now flux cut per conductor in one revolution is d pi. Okay, here d pi is the flux cut by the conductor in one revolution and dt is the time taken by the conductor to complete one revolution. Okay, according to the Faraday's law of electromagnetic induction, the average EMF generated per conductor equals to d pi by dt. d pi is the flux cut by the conductor in one revolution and dt is the time taken by the conductor to complete one revolution. Okay, so the number of revolutions, here we know that assumption, the speed of the armature equals to capital A and RPM. So RPM means revolutions per minute. So the revolutions per second equals to n by 60. Revolutions per minute equals to n. Revolutions per second equals to n by 60. So next one, so one revolution time. So 1 second number of revolutions equals to n by 60. So one revolution time equals to 60 by n seconds. Okay, this is dt. So next one d pi. So d pi means the flux cut by the conductor in one revolution. So here we assumed the number of poles equals to p. So the conductor cuts the total flux inside the generator. So pi is the magnetic flux produced by the each pole. So the total magnetic flux present in generator equals to pi into p. Okay. The total flux inside the generator equals to pi into p. So total number of poles of generator equals to p. The flux produced by the each pole equals to pi. So total flux inside the generator equals to pi into p. So in one revolution, the conductor cuts the total flux inside the generator. So it equals to pi into p. So d pi value equals to pi into p. So EMF generated per conductor equals to d pi by dt. It equals to pi p. D pi equals to pi p and dt equals to 60 by n. 60 by n. So finally we get pi pn by 60 volts. So number of conductors in one parallel path. Okay, we know that capital A is the number of parallel paths in armature winding. So one parallel path number of conductors equals to Z by A. The total number of conductors equals to Z, number of parallel paths equals to A. So one parallel path conductors equals to Z by A. So EMF generated in one parallel path equals to pi pn by 60, pi pn by 60 into Z by A. Okay. So generated EMF equals to, we can write pi Zn by 60 into P by A. So this is the DC generator EMF equation. So the generated EMF equals to pi Zn by 60 into P by A. So we know that the armature winding having two types of winding, wave winding and lap winding. If it is wave winding, the number of parallel paths, A value equals to 2. If it is a lap winding, the number of parallel paths, A equals to P. Okay, next topic, the total losses in DC machine. Okay, the total losses in DC machine are divided into mainly three types. First one copper losses, second one iron losses, third one mechanical losses. Okay, these losses are due to windings. These losses are due to core. Next, these losses are due to bearings and air gap. So total losses equals to copper losses plus iron losses plus mechanical losses. Okay, again these copper losses are divided into, we know that in generator three types of windings are there: armature winding, series field winding, shunt field winding, and these windings are made up of copper material. So three types of copper losses. So first one armature copper losses, second one shunt copper losses, third one series copper losses. So next one iron losses. The iron losses are divided into two types: hysteresis losses, next one eddy current losses. So next one, mechanical losses. Mechanical losses are two types, frictional losses, next one windage losses. Okay. So total losses in a DC machine are copper losses, iron losses, mechanical losses. So copper losses are mainly due to current passing through the winding. Copper losses are divided into three types: armature copper losses, shunt field winding copper losses, series field winding copper losses. In total losses, 30 to 40% of losses are due to armature copper losses. 20 to 30% of losses are due to shunt field winding copper losses. So series field winding copper losses are less. So approximately 10 to 20% of full load copper losses. So first armature copper losses. So copper losses equals to formula current square into resistance, I square into R. So first one, armature copper losses, it equals to armature current square into armature resistance, IA square into RA. Here RA is called armature resistance, IA is called armature current. Okay. So next one, shunt field copper losses. So shunt field copper loss equals to shunt field current square into shunt field winding resistance. So it equals to ISH square into RSH. Here RSH is shunt field resistance, ISH is shunt field current. So similarly, series field copper losses. Series field copper losses equals to series field current square into series field winding resistance, ISC square into RSC. Here ISC is series field winding current, RSC is series field winding resistance. The armature copper losses are also called as I square into R losses. So next one, iron losses. So iron losses are also called as magnetic losses. So these losses are approximately 20 to 30% of full load copper losses. The iron losses are divided into two types, hysteresis losses, next one eddy current losses. The hysteresis losses are represented by W suffix H. So mainly these losses are due to reversal of magnetization of the armature core. The every portion of the rotating core passes under north pole and south pole alternatively, so thereby attaining south and north polarity respectively. So due to the magnetic reversal, these hysteresis losses are produced in cores, armature core and field core. So the hysteresis losses equals to mu into B power 1.6 into B maximum power 1.6 F into V watts. Here F is frequency, it equals to Pn by 120. So V is volume of the core and B is magnetic flux density and it is constant value. Mu is constant value, units are watts. So the hysteresis losses are generated due to magnetic reversal. Hysteresis losses formula. So the hysteresis losses can be reduced by using silicon steel material. Okay, generally the cores are made up of silicon steel material. So approximately 4% of silica is added to steel material. So it is called silica steel material. So by using silicon steel material, we can reduce the hysteresis losses. So next one, eddy current losses. This is represented by W suffix E. So when the armature core rotates, it cuts the magnetic flux, hence an EMF induced in the body of the core according to Faraday's law of electromagnetic induction. So this EMF through small sets of large current in the body of core due to small resistance. This current is known as eddy current. Okay, we know that the armature conductors are located in armature core. So the armature conductor cuts the magnetic field. So finally EMF is generated inside the conductor. So our requirement, the EMF must be generated inside the conductor. So but the armature conductors are placed in armature core. So armature core also one type of conductor. So with armature conductors, armature core also rotates in a magnetic field. So armature core also cuts the magnetic flux lines. So finally the EMF is generated inside the armature core. So due to this armature core EMF, some currents are flowing through armature core. These currents are called eddy current. The losses due to these eddy currents are called eddy current losses. The eddy current losses can be reduced by using laminations. The armature core and field cores are made up of some laminations. Okay. So by using this lamination, we can reduce these eddy current losses. The eddy current loss is equals to formula K into B maximum square into F square T square into V square watts. Here B maximum is maximum flux density, F is frequency of the magnetic reversal, V is volume of the armature core, and T is thickness of the lamination. Okay. The armature core and field cores are not solid structures, so which are made up of laminations to reduce the eddy current losses. So eddy current losses is directly proportional to the thickness square. Okay, thickness of the lamination square. Okay, next one, mechanical losses. These mechanical losses are approximately 10 to 20% of full load losses. The mechanical losses are divided into two types: frictional losses and windage losses. The frictional losses are due to bearings. Okay, we know that inside the generator, for smooth operation, we are using bearings. So, but bearings also having some losses. The losses due to bearings are called frictional losses. So, next one, windage losses. Okay, we know that the gap is present between armature core and field core. Okay, so due to this air gap, these windage losses are produced. Okay, finally we can say that the total loss is equals to copper losses plus iron losses plus mechanical losses. Copper losses are three types: armature copper losses, series field winding copper losses, shunt field winding copper losses. Mechanical losses are divided into two types. So first one, frictional losses, second one, windage losses. Iron losses are divided into two types: hysteresis losses and eddy current losses.